our next presentation, Tenstorrent will be presenting information on their next generation product that they're introducing here at our conference. Making the presentation, we have Drago Ignjatovic, who is the Vice President of Silicon Engineering, where he leads the processor design team. He's been involved with the development of all the Tenstorrent processors to date, and prior to that, he spent 11 years at AMD. He'll be joined by Davor Capalija, who's a fellow at Tenstorrent, where he leads the architecture and advanced development team that contributes to both hardware and software at the company. They'll be presenting a scale-out first microarchitecture for efficient AI training. Take it away, Drago.
Hello and welcome to our presentation. My name is Drago Ignjatovic, and I'm the VP of Hardware Engineering at Tenstorrent. I would also like to introduce Davor Capalija, a fellow at Tenstorrent. Today, I have the pleasure of introducing our new product, Wormhole. After that, I will hand it over to Davor, who will talk about the microarchitecture underpinning Wormhole, specifically tailored for large scale-outs. Let me start with a very short history. Drawbridge was our first silicon. It's a test chip meant as a proof of our architecture and performance claims. Drawbridge introduced our SoC architecture, an array of 10-6 processor cores, surrounded by memory, LPDDR4 in this case, and I/O, PCIe Gen 4. All connectivity within the chip is over our NOC. This architecture is carried forward to all of our silicon. Grayskull is our first product. It came back to our lab in late 2019, and for the past year has been sampled by multiple customers. It is currently in production with A0 silicon. Grayskull has 120 10-6 cores, 8 channels of LPDDR4 and PCIe Gen 4, along with a host ARC CPU. Today, we're introducing Wormhole. Wormhole has some key upgrades, specifically targeting AI training. It also has faster memory and Ethernet for chip-to-chip and chip-to-switch connectivity. I'm very happy to say the Wormhole came back to our lab about a month ago, and that all functional blocks, including DDR, PCIe, Ethernet, as well as the processor array, are up and running. This is the actual Wormhole floor plan. As already mentioned, the SoC architecture follows the path set forth by Drawbridge and Grayskull. Wormhole has 80 10-6 cores, 6 channels of GDDR6, 16 lanes of PCI Express Gen 4, and 16 ports of 100 gigabit Ethernet, all of it connected through our NOC. Along with the obvious changes I just mentioned, we focused on other key improvements as well, increasing compute performance as well as general PPA improvements. Furthermore, Wormhole is also a native Ethernet packet switch, which is a crucial differentiator at system level. Let me give a high-level overview of the silicon features. On the 10-6 processor core side, we've increased the math throughput per 10-6 core. We improved our SIMD engine and added the ability to execute complex math and logical instructions. We also increased the amount of SRAM per 10-6 core in order to efficiently feed compute blocks. On the SoC side, like I already mentioned, GDDR6 memory with 384 gigabytes per second of total bandwidth, 1600 gigabit Ethernet ports for a total of 400 gigabytes per second of bandwidth. Importantly, Ethernet ports act as a native NOC extension, allowing data transfers chip to chip to require zero software overhead. This, along with the packet switching capability of our NOC, makes Wormhole extremely powerful for building large scale-out systems. We've paid particular attention to system-level architecture with Wormhole. AI training workloads are growing in size, and they already span multiple servers and racks. Unlimited scale-out capability is a must today. This was an important consideration for Wormhole. We plan to productize Wormhole both as an add-in PCIe card, but more importantly as a Wormhole module. The module consists of a Wormhole chip plus 6 GDDR6 memories. It also brings out all 16 Ethernet ports to the board with 4 ports on each side of the module, as you can see in the diagram. Using the Wormhole module, we've designed Nebula, a 4U rack server containing a grid of 32 Wormhole chips. Within the server, Wormhole chips are connected in a full mesh with 100 gigabytes per second of Ethernet bandwidth on each side. The modules on the edges obviously do not have all of their Ethernet ports used in this case, and they can be connected to switches or more Nebula servers for further expansion. Within a Nebula server, we have 384 gigabytes of DRAM and over a terabyte per second of Ethernet connectivity available to the outside world. Moving on to the rack, Galaxy is a 48U rack with 8 fully connected Nebula servers. It also has general purpose compute and the memory pool for larger workloads. The general purpose 2U servers and memory pool are all connected over Ethernet to the Nebula servers. Similarly, Nebula servers within themselves or in between themselves are also connected directly over Ethernet. I will show the server-to-server connectivity within the rack, but first a different configuration for the 48U rack. With less compute power, only 4 Nebulas in this case, but a much larger memory pool to gear it towards specific workloads, such as recommender systems in this case. Here's a full 48U rack unrolled in what we call supercomputer topology. As you can see, it is connected like a 2D mesh, with each wormhole on an edge of one server connected directly to its counterpart on the next server. Thus, to software, the entire rack looks like a large homogeneous mesh of wormhole modules, and importantly, 10.6 cores within them. It is important to note, and I'll show it later, that we support other topologies as well. And finally, rack level connectivity. Wormhole is extremely flexible in this regard as well. This is again supercomputer topology, a fully connected rack-to-rack system, which simply just extends the grid in a uniform way. Similar to connectivity on a single rack level, in this topology, wormhole modules on the edges of one rack are connected directly to their counterparts on the next rack. You can imagine that the grid can be extended even further in either X or Y dimension, practically to infinity. This provides full bandwidth to each processor in the array and has uniform bandwidth across the mesh. And because Wormhole has a built-in switch, the supercomputer topology does not require expensive switches. In fact, the top of rack switch is only used for connection to the outside world. A different option is a more traditional data center topology. There's less bandwidth between the racks, but still a uniform grid and exactly the same connectivity. All nebulas are connected through a top of rack switch plugged into a data center network. With this topology, there is definitely a bandwidth hierarchy. Chip to chip is full bandwidth, but server to server and rack to rack are penalized. However, the benefit of this topology is that it is elastic, it supports multi-tenancy and redundancy more readily. Wormhole is designed to be completely flexible in scale-out connectivity without impacting the software view of the system. Thus, chip-to-chip, server-to-server, and rack-to-rack topology and bandwidth can be optimized to the workload, cost, size, or any other parameter important to the system builder. I will now hand it over to Davor, who will share the details of our scale-out microarchitecture and how our software will utilize the system. Thank you.
Thanks, Drago, for the great overview of the hardware. So I'll switch gears a bit now, and I'll talk about how Wormhole enables deep learning scaling. So what that means is really scaling the size of AI models to trillions of parameters, and efficiently utilizing tens of thousands to hundreds of thousands of chips in a cost-effective manner. So it may seem that you can go about this by just adding lots of servers and putting lots of racks together. However, what that just creates is basically a lot of these hierarchies across from core to chip to server, both on bandwidth and the programming model. There's one programming model for core, for chip, and then there's different bandwidth as you go from chip to server to rack. So this is just a sort of naive brute force way of adding more compute. Is really hard to utilize, if not impossible, for both compiler designers and for model designers, right? They're just really constrained by the hardware and these hierarchies of the physical hardware, and they more end up just hand tuning the model to reflect the hardware, as opposed to actually being free to design the model that they want, and also be able to do this automatically. So the more complicated these hierarchies, the more complicated compiler design becomes, and a lot of these things are not really automated. So really, our goal was to design a microarchitecture from ground up, from scale out, such that these strict hierarchies that I mentioned are removed, such that as you just add more cores and servers, the view that is presented to the model designer or the programmer is just an infinite mesh of cores. So on one hand, that now will unconstrain the model designer in how they think about the model and what the model should look like. It doesn't really need to reflect the hardware. It's just a uniform hardware. And on the other hand, the compiler can now do an automated place and route. So in the following slides, we'll go deeper into how we actually achieve that. But before we go there, let's just quickly review a bit of history of scaling deep learning on the sort of legacy hardware. So the way really it started is with batch-based data parallelism on CPU clusters. Just have a big batch size, split it across the CPUs in a cluster, have a central parameter server. This really didn't scale well at all. And then this was improved using a cluster of GPUs, and you had an all reduced, a bit more bandwidth between these GPUs. So that drove progress for a couple of years. It got us to ResNet and BERT breakthroughs. This approach does have limitations, and even back in the day, there were early attempts called disbelief framework to combine other types of parallelism as opposed to just increasing the batch size, splitting, sharding it across the cluster. So just probably a lot of you are familiar with this. Just a quick recap, won't spend too much time. So limitations of just this batch-based parallelism is at some point you just run out of batch size. You'll just let hit the batch limit. The model won't converge, won't get good accuracy as you keep doing this. So and as the model gets bigger, ultimately you run out of single node DRAM capacity as the model just gets replicated across all the nodes. In order to do that, you just need to have lots of DRAM, and then the model obviously won't fit. The intermediates won't fit into SRAM. Therefore, you would need to have lots of bandwidth to this DRAM now. So now you have lots of DRAM and lots of bandwidth, ends up being really, really expensive. Really, for example, you need to really have expensive HBM. So ultimately, you can do this for small model training, which is a couple of nodes, but scaling this to 10,000, 100,000 is really not cost effective and ultimately won't give good performance. So it's not a surprise that we're seeing an emergence of different approaches and different types of parallelism. So I'm showing here a bunch of frameworks that exist in the industry that allow the user to specify and combine model, pipeline, and sharded data parallelism effectively to distribute the model across the cluster. So the model doesn't need to fit into one node, and you don't need to have replicating the model, increasing the batch size. You actually just are able to spread across. Today, this is done really manually, but there is at least a trend showing that this is the way to do things going forward, especially towards trillion parameter models. So with this vision in mind, that we really want to spread the model across the cluster, how do we do this? And what will we need from our microarchitecture? So switching gears onto Tenstorrent microarchitecture. So it was really built for place and route of graphs of mini-tensor, or as we like to call it, as natively execute graphs of mini-tensors. And what are mini-tensors and why? So if you look at pipeline and model parallelism, pipeline parallelism will slice the graph into pieces, and those pieces need to be laid out across cores, chips, servers. But similarly, if you look at in tensors in these graphs, and as you scale up the model size, these tensors become bigger and bigger, and you need to slice them in order to fit them into memories of the cores. And these slices we call mini tensors. So what this leads to is placement of mini tensor operations across the cores. On the other hand, these operations need to be connected together, and often there will be some reshuffle of these mini tensors, such as reshape or transpose. So if you want to connect these operations now on mini tensors, what this leads is to routing of mini tensors between the cores. So together that you get place and route of mini tensors across the fabric. So our goal was let's design an architecture that can natively run such graphs that have operations on these mini tensors. And let's do this in the most efficient, high performance way, but at the same time, it needs to be easy to program in order to actually be able to use this really high performance architecture. So we started with an assumption, let's say have a mesh of compute blocks and memories, and then interconnect that works both within the chip and across the chips. So what's the functionality of these blocks, and what's the best granularity in order to achieve both the programmability goals and the efficiency? So in order to make this microarchitecture efficient and tuned for AI, we made these mini tensors that I just described, the native data type of the architecture. So everything is realized as a as everything that's realized is a mini tensor. But all the components architecture speak these mini tensors, and we call them also packets. So it's a packet because to a mini tensor, we just attach a header, and now that header is used to route these mini tensors within the chip and across the chip. So what I'm showing here is you have a tensor, 10-6 core and an interconnect network or chip between these cores. These mini tensors will flow on the network or chip. Then between the chips, we have Ethernet, as Drago described, and this Ethernet acts as a NOC extension, and the packets that go over this Ethernet are a very close match to our internal mini tensor packets. So it's basically a NOC extension. I'll describe in a bit more detail next slide, but NOC is also an integrated switch. So on the compute side, everything also speaks mini tensor packets. What that means is that the 10-6 core can directly ingest and process these packets. We won't go into details in this presentation on the compute side, but basically the key is that the router packet manager deals with all the synchronization and movement of the mini tensors, whereas the matrix vector engine directly computes on these mini tensors and outputs them back into the node. So from the software perspective, transfer of mini tensor packets between any two cores looks the same. And so in this example, 3 mini tensors are transferred between 2 cores on different chips. And what compiler and programmer sees here is just a uniform mesh interconnected across the chips. So there's 8 chips, but the programmer sees a uniform a mesh, of course, and the sending from cores on different chips is the same as sending between cores in the same chip. So the packets can pass through the intermediate wormhole that we're showing here, because this intermediate wormhole acts as a switch because our network on chip has built-in switch capability. So as you can see here, there is, in order to route packets across any of 2 wormholes here, we don't need any additional switching or any additional hardware. Everything is realized here. The compute and the interconnect and the switching just using the wormhole chips, which we believe is a really cost-effective way to scale out. And so for software, in this example, this is just seen as pushing the packets on one core and popping them on the other core. So these are some of the key primitives, this pushing and pop of tensors, and that's as a way of moving tensors between the cores. But there's other mini tensor primitives that we support with 0 performance overhead, such as copy of mini tensor, gathering of tensor, scatter, shuffle, both in unicast and multicast modes, depending on the consumer-producer relationship in the graphs. So you can look at this both ways. You can compose these primitives together to build up a graph of mini tensors, or compiler can take PyTorch or TensorFlow and then lower it into graph that's composed out of these primitives that ultimately runs on the hardware with 0 overhead. So now putting it all together, I'm showing a diagram that Drago already showed, which is there was 2 racks and 16 servers for a mesh of 16 by 32 chips. So that's sort of the physical view of this hardware. But we really want to present is a uniform mesh substrate that then can be used for model and pipeline parallelism. So really, all of the hierarchies of core chip server here are actually removed. So on this diagram of 16 by 32 chips, the bandwidth between the neighboring wormhole chips is the same no matter where you are in this mesh. So there is really no notion where is the rack boundary, where is the server boundary, right? And as I mentioned before, there is no need for switches because wormhole then sends our switches so they can just route the packets between them. There's alternate view is the zooming in into the cores and looking this as a 160 by 256 cores mesh. In order to grow this mesh, just more racks and more server need to be added, and as a result, you get a bigger mesh. So with that, if you want to map model and pipeline parallelism in a flexible way, you don't really need to worry about any of these boundaries. So intentionally, I'm showing the boundaries here just to show how they can just you can cross, the layers can cross these boundaries. So an example in model and mapping of model in example 1, layer 2 and layer 6, they are mapped on 2 servers, but these servers are across 2 different racks. The layers can use arbitrary number of resources to match their actual compute needs. So layers will be sized differently depending on their needs. So for example, layer 11 in example 3 is just using half a server, but layer 10 is using 1.5 server, just as if this was a uniform grid of chips. And on model 4, one really big layer is spanning across 2 racks. So this was an example with 2 racks, but this can be extended to a mesh that has 10 or 16, 40 or 100 racks. It just represents a bigger mesh of chips and cores. So to summarize the key aspects of our microarchitecture, I'll compare to other mesh architectures and to really highlight the why our architecture is special. So we have FPGAs and CG arrays. They're both mesh architectures. FPGAs were made for circuit graphs. FPGAs have lots and just map a netlist. So they really work at the very fine grain level. CG arrays work at slightly higher granularity. They have ALUs and they run scalar graphs. And they're smaller memories and they route wires, and the CG arrays will route words. So on the other hand, in the Tenstorrent microarchitecture, as we mentioned, there's big cores, couple of teraflop, matrix engine, bigger memories, and both the NOC and the interconnect between the chips is packet-based and natively speaks our packet mini-tensor based interconnect. So so for 2 reasons, our architecture here stands out. First, it's much more efficient because the blocks are efficiently designed for AI. But on the other hand, it was from ground up designed for scale out, such that within the chip and across the chip, the interconnect is the same and works in the same packets, which is not the case for other mesh architectures. I'll summarize now. So as Drago introduced the Wormhole chip at the beginning of the presentation with a range of silicon improvements to previous generation, and it can achieve efficient scale out with Ethernet interfaces, an integrated internal switch across chips, servers, and racks connected in flexible in a range of topologies. When connected in a supercomputer topology, we provide a uniform mesh substrate for compiler across chip, server, and rack hierarchies, and that simplifies compiler design and model design. And mini tensor graphs are composed out of built-in data flow primitives with 0 performance overhead, and this enables unconstrained pipeline model parallelism. So Wormhole is currently in the lab, and all functionality has been brought up, and sampling is starting middle 2021. So that concludes the presentation. Thank you.